My name is Andrew Hirsch. I'm a postdoc at the Max Planck Institute for Software Systems, and I'm here today to tell you about some work I've done with my colleague Ethan Cecchetti of Cornell Computer Science. In computer science, we're often interested in properties of programs. In particular, we're often interested in security properties, such as non-interference. A lot of the work done here at FCS and CSF is on designing type systems for information flow control security. These guarantee that if a program type checks, then it's non-interferent. However, a lot of the programs that actually get run are not the programs that we type check. Instead, they've undergone syntactic transformations. We do this for lots of reasons, including optimization, obfuscation to avoid intellectual property theft, and perhaps many other reasons as well. However, no matter the reason, we want to know, did we get the transformation right? In particular, did we destroy non-interference? It turns out it's often easier to actually ask the question, is the program that I got out of that transformation the same as the program I put in? Now, clearly, I don't mean syntactic equality. If we did syntactic equality, we wouldn't have done a syntactic program transformation, but semantic equality of some sort. And that means that our semantic equality needs to be with respect to some model. In this talk, we're going to be looking at how we build models of information flow control type systems, and in particular, at how the program counter is treated in such models. To start with, let's see how the program counter works in an information flow control type system. Imagine we're working with a language with a single cell of memory, X, which is publicly available. We're also going to keep track of the program counter as we would be type checking the program. The program counter always starts as public. Now imagine that we have the simple program where X gets a public integer, say 3. In this case, this program would type check because public data can go into a public memory cell, and when we run it, we put 3 in the memory cell and get nothing interesting. In this case, we output unit, as is common in functional programming languages, but in imperative languages, often just nothing is output at all. The program counter becomes useful when we look at more complicated programs that include branches. For instance, this program branches on some private data and then stores a different public integer in the memory cell X, depending on the branch. When we type check this, we have to examine the branch X gets 3 at a public level, which is the same as with the program we saw before that type checked fong. However, now the program counter is private. One principle of information flow security that comes up in this case is that public memory cannot change based on private decisions. Therefore, we must not be able to type check and therefore not run this program. This gives rise to 2 perspectives on the program counter label. In the first perspective, the label is used to keep track of the data that is used to decide on the program path. We're not allowed to take actions that would reveal the program path if the program path was decided upon using private data. In the other perspective, the program counter bounds the effects of the program. This is because the effects are the actions that can reveal the program path. While both these perspectives are correct, the second perspective turns out to be more useful in building our model. With this perspective in mind, we can consider again this leaky program, which we saw earlier. We need a PC to catch the leaking. Now, however, let's consider examining the effects, and we do that using a monadic interpretation. Monadic interpretations are the standard semantics of effects that appear in the PL literature. And what they do in this case is make the new state part of the return value. This is interesting because now we can catch the leak in this program without using a program counter. This is because changes to the state are now different return values, and we can catch when a program returns different values based on private inputs without using a program counter. While we needed a PC to catch the original program, we never used the PC to catch this program or to do the translation. So this seems like it is giving us a big insight into how the PC is being used to bound effects. With this insight, we now have some idea about how to build a model for program counters. We start with an information flow control system that includes a program counter label. We then give that semantics in terms of a type and effect system. While others have suggested before that the program counter label bounds effects, nobody's actually formalized that through a type and effect system. We then give the type and effect system semantics via monadic interpretation. This is mostly standard. Type and effect systems are given semantics via monadic interpretations all the time in the PL literature. However, here we have to make non-trivial changes to account for the security of the system. These changes allow us to make our semantics of the program counter in terms of the type and effect system extremely simple. In order to understand the monadic interpretation, including the changes we have to make for security, we have to understand programs as things that take inputs and produce outputs. Therefore, I'm going to be using this sort of machine diagram you may have seen before in high school or whenever you learned mathematical functions for the first time. Our program P here takes inputs of type tau. Notice that type tau can have a label L. It then produces outputs of type tau prime. P is non-interferent if anyone who can see tau prime can see things labeled L. Thus, if some adversary, say Alice, comes along and wants to know what the output value is, they have to view that output value through their lens. If they can see the output value through that lens, then they would have been able to see the input as well. However, our programs are not mathematical functions. They also produce effects, say epsilon. And the PC is somehow embedded in our program, and it guarantees that anyone who can see the effect can also see things labeled L. Thus, if Alice wants to know what effects happened, she can only tell if she would have been able to see the input of the program. Everything so far has been very standard information flow control. What the monadic semantics does is it doesn't keep track of a program counter. Instead, it makes the effect part of the output type. The big security change we make is to take these two previous information flow control guarantees and combine them into a new guarantee that anyone who can see the new output type can also see the inputs. Formalizing this simple insight gives the key rule in our semantics. Of course, this doesn't work on its own. Supporting rules are necessary to back it up. Sadly, I'm not going to have time to talk about the supporting rules in this talk, so you should look at our paper. So, we now have our model, and we know what the key rule is in this bottom transformation. Interestingly, what this does is it guarantees that everything in the type and effect system is secure. Thus, we can give the following semantics to the PC system, which is incredibly simple. If a program type checks in the PC system, then there is an effect such that the program type checks with that effect. In other words, the role of the program counter label is to restrict our language to programs with secure effects. These are the key ideas behind our model. We've also explored some of the nice consequences that our model gives us. Imagine that our friend here has designed an information flow control type system, and he wants to prove non-interference for that system. Now, he observes that in his language, like most languages, there's a pure sublanguage, and non-interference is much easier to prove for this pure sublanguage. You don't even have to keep track of the program counter label. What our model suggests you can do is use a monadic interpretation of the effects in his full language, and thus only need to prove non-interference for the pure language. Moreover, this also gives him access to other results about monadic effects, such as results about optimization. We refer to this proof technique as non-interference half-off because you only have to prove non-interference for the pure sublanguage, a much simpler job. Moreover, if our friend is concerned about termination sensitivity, he can prove his language termination sensitive by using a non-termination monad as part of his effect. Putting it all together, we've developed a new model for information flow control type systems, and in particular for program counters. This led to a new proof technique, non-interference half-off, as well as connections between information flow control and monadic semantics, an increasingly common technique in the programming languages literature. Finally, it allowed us to unify several previously disparate notions in the information flow control community, such as the treatment of read and write effects, the treatment of exceptions, and termination sensitivity. At this point, I'd like to thank you and take any questions you may have.